In this video, we're going to be talking about Rolle's theorem. Rolle's theorem here is what theorem 3.3 says. It says let f be continuous on the closed interval a to b and differentiable on the open interval from a to b. So you can take the derivative of it, and it's continuous on the interval that we're talking to, which means it doesn't have any jumps or anything like that. It's not undefined at any point. If it says that at some point f of a equals f of b, so what it's saying is basically if I start over here at some point A and end at some point B, if that's my interval, they're saying we have a y value that's the same, and I'll just say it right here, and it can do whatever it wants in between here and do whatever. But as long as it ends here and here, all right, what's Rolle's theorem? This is continuous and all that. If it's continuous and differentiable, then we know for a fact that there has to be a point, some point C, so some point in here, basically here, there's going to be a minimum or a maximum or something like that, where the derivative is going to equal 0. All right, so the three conditions that must apply. All right, it has to be continuous on a closed interval. All right, so if I, instead of scribbling like my last graph, show you an actual probably graph. All right, say that they two equal, and it's possible, very possible, we can get a graph like that. All right, on a closed interval. Okay, so it's obviously it's continuous. I don't have any jumps anywhere. The second case, f is differentiable on the open interval. So I guess if I were to continue this out, can we take the derivative of that function? Sure can. And then the last part is during our interval is our a point. Say we're looking at this interval here and here is our a point. At a is it the same value for b? Is the y value the same value? So those are the three conditions for Rolle's theorem. All right. So an if those theorem was to apply, we know that there must be at one point where basically the graph changes direction, and hopefully that makes sense to you. If I'm going to start up here and I got to get on my graph, I'm going to start up here and I got to get back to some point that's that same y value, I obviously have to change directions, right? So my derivative of my tangent line has to be 0 at some point. All right. So here we're going to do a little illustration of what Rolle's theorem is saying here. Example 1, it says find the two x-intercepts, all right, of this function here, x squared minus 3x plus 2, and show that the derivative equals 0 at some point between those two intercepts. Okay, so we're going to find the x-intercept of x squared minus 3x plus 2. Well, the x-intercept's when y equals 0, right? So we're going to say 0 equals x squared minus 3x plus 2. To solve for x, it looks like we're going to have to factor. We're going to have to factor. Looks like it's going to be x. It's going to be multiplied 2, add up to be a negative 3. This means same sign. They're both going to be negative. So minus 2 minus 1. Be what that factors down into. So I know my x-intercepts where x or y equals 0 is going to be at x equal to 2 and x equal to 1. So I have some graph. All right. And we can graph this. We learned how to graph this last year in pre-calculus, but we have some graph where it has a x-intercept at 1 and an x-intercept at 2. Well, we know this graph is going to look something like it's an even function, so it looks something like a parabola. So what we're doing is Rolle's theorem. We said at some point, all right, our y values have to be the same. Here would be like my a, and here would be my b. Okay, so at some point they're the same. We know that this graph has to change direction. We know at some point, or maybe 2 points or 3 points, that graph needs to change directions to get back to 0. So we started at 0 here. At some point, it's got to change directions to get back to 0 here. So we know for a fact it's continuous. This function is continuous. That condition holds. It's differentiable. We can take the derivative and find a value on all points. So Rolle's theorem holds, so we know for a fact that we should be able to take the derivative and figure out that there's a point where the derivative is going to equal 0. So I'm going to take the derivative and get 2x minus 3. And we know by Rolle's theorem that that has to at some point equal 0, so we'll solve for x. So we get x equal to 3/2. So at x equal to 3/2, we're going to have a point there, whatever the y, we can figure out the y by plug it back in, but we know that at x equal to 3/2, that graph is going to change directions and head up back towards 0. All right? The slope of the tangent line is also 0. Okay, and this last one again, we're going to do the same thing. Find all values of c in the interval from -2 and 2 such that f prime equals c, or f prime of c equals 0. Well, first of all, we better check whether there is going to be one. We'll save us some work. So let's see if our first condition holds. All right, are the y values for these two, I mean, these are our two closed. All right, so we're going from we're looking at the point from -2 to 2. All right, are those two going to equal the same? Are the y values going to equal the same? Well, I plug -2 in. -2 to the 4th power is going to be 16 minus 8. So we're at -2, we're going to have a point 8. And at +2, we're also going to have a point, well, 16 minus 8, 8. So we're going to have 2, 8. So the 1 holds, so f of a equals f of b. That's good. All right. Is this function continuous? Well, it looks like a parabola. I don't see anywhere where it's not defined. It is continuous. And is it differentiable? Are we going to be able to take a derivative and find all values? The tangent line, yes, we can. All right. So we know that there's going to be a value. By Rolle's theorem, we know that there is going to be a derivative where it's going to equal 0. The slope of the tangent line is going to equal 0. So let's find out where those points are at by taking the derivative. So f prime of x is going to equal 4x cubed minus 4x. And then we know by Rolle's theorem that we want it to equal 0 at some point. So we're going to have 0 equals, while I'm at it, we might as well factor out a 4x, right? So 4x times x squared minus 1. So it looks like we're going to have, if we solve this, all right, well, we set this one equal to 0 and we set this one equal to 0, and that would solve our equation, right? Okay, so it looks like my solutions for this is going to be x equal to 0, and I'm going to have more than one. I'm going to have x squared minus 1 equals 0. We add 1 over and take the square root, so I'm going to have x equals a positive 1 and x equals a negative 1. So I actually have 3 points on that line where the slope of the tangent line is going to equal 0. All's Rolle theorem guaranteed is we're going to have one of them, and we could certainly have more like we just had there. All right. So there's Rolle's theorem, and it's a pretty short assignment today. I hope it makes sense. We'll see you in class tomorrow.